Welcome class to this video on interpreting a distance time graph. In this video I'm going to be introducing distance time graphs to you and teaching you how to interpret them, obviously from the title of the video. To do that I'm going to be using what you see on the screen. This is called a gizmo, and I've provided for you in the assignment a username and password that you can use to access this little gizmo if you choose to as well. You should also have with you a handout that you're going to fill out as we go along in this video. And as you will see in this video, there are some embedded questions that you will be expected to answer. So make sure you're paying attention. All right, so let's jump right in. The first thing I want to point out to you about a distance time graph is that the y-axis of a distance time graph is the distance traveled from a fixed point, and the x-axis is the time taken from the start. All right, so you should fill that first point in on your handout. The y-axis of a distance time graph is the distance traveled. The x-axis is the time taken. Now it says from a fixed point, and that's good to contemplate as well. If you see here, it says distance from starting line. So in this distance time graph, our fixed point is the starting line, and the distance this person is going to travel once we start to track his motion will be either away from or toward that fixed point. On to our next point, which is that if the vertical axis is labeled, for example, distance from starting line, as you can see the vertical axis here being labeled, a line going upward to the right means an object or person is moving away from the starting line. So, as I just said, we have here distance from the starting line. We have here a line that is going up to the right. This line reflects the idea that when we show this person's movement is going to be away from the starting line. Okay, so I'm going to press the green button here. We can watch the person move, and we can see how the graph reflects his movement. What you should have observed there is that he started at 0 meters away from the starting line, right? Do you see this is 0, 0? This means at 0 seconds, the person is 0 meters away from the starting line. If you are 0 meters away from something, it means you are at that thing. So he was 0 meters away from the starting line at the beginning. He then ran for 4 seconds. You can see 4 seconds has elapsed here on the x-axis, and he ended up 40 meters away from the starting line. So a line going up to the right reflects the idea that the person or object is moving away from the fixed point. In this case, the fixed point is the starting line. Now, a fixed point could be a home, a locker, a motion sensor. It could be anything that you decide is where you're going to start measuring the person's distance from. All right, so now we need to consider something else. What if we have a line that is going downward to the right? So I'm going to put this person back at the start. What if we had a graph that looked like this? We know this part of the line that's going upward to the right represents that they're moving away from the starting line. What will this line represent over here? Let's take a look. As you can see, the person ran away from the starting line. They ran away till they got 40 meters away from the starting line, and then what did they do? They turned around and they ran back. And so when you have a line going downward to the right, it means an object or person is moving toward the starting line. Our next point on our handout is that a straight line denotes a blank speed. And as you can see on our graph, we only have straight lines. And unfortunately, that is the limit of this tool. I can only show you straight lines. What a straight line means on a distance time graph is that the speed is constant. So a straight line denotes a constant speed. And so if you watch as this person runs, what you will notice is they're doing the same speed throughout the entire graph for each line. Now in this, I have two lines which are the same steepness, and so both of these lines are going to represent the same constant speeds. The speed is not changing. Now, since our gizmo cannot show us curved lines, I thought I'd show you two representations here of curved lines in a graph that can denote that a speed is changing over time. And so if you look on the left, you can see there's a graph which shows an increasing speed, and the technical name for that increasing speed is acceleration. And you can see that the line is curving upward. It's curving upward, and it's becoming closer and closer to becoming a vertical line. Now, it can never actually become a true vertical line. And the reason for that is, well, think about it for a moment. It would mean that the time had stopped moving. Time is no longer moving, right? Because time is moving, would be moving along the x-axis like this. The line is going this way as time is passing. But if the line is completely vertical, time is no longer passing, and yet somehow the person or object's distance is increasing. That is very difficult to contemplate, and you will never, as a result, see a vertical line on a distance time graph. Okay, but what you should be understanding exactly is that this curved line represents that the speed is changing over time. The speed is not constant. And if the line is becoming closer and closer to becoming vertical, that means the speed is increasing. That's called acceleration. Now, the other possibility is that you have a line which is decreasing, becoming closer and closer to vertical going downward. So you see, this also could show increasing speed, just in the opposite direction, right? So whereas the first, this red line here, which is curving upward, was going away from the fixed point, the curve downward is increasing speed towards the fixed point. Now, looking at the other graph on the right here, again we see a curved line which denotes a speed that is changing over time. However, this time we're seeing a speed which is decreasing, and the technical name for that is deceleration. And what you should notice in this line is that the line is getting closer and closer to becoming a horizontal line. Closer and closer to becoming a horizontal line. And if it becomes actually horizontal, what that would mean is that the person had stopped moving. Okay? And so this would mean time was still passing, but their distance was no longer increasing. Therefore, they had stopped moving. Now, there is one other possibility, and that other possibility is that the person is running around a fixed point in a perfect circle. And this would mean their distance from this fixed point here in the middle would never change as they went around the fixed point in a perfect circle. Okay, now that's actually just really just an exception. Normally, when we talk about a line being horizontal, it will mean that the person has stopped moving. So just to show you this decreasing speed in the other direction, so again, this line is moving away from the fixed point, but you could have a curved line, for example, that was like this, and this would also represent, as it got less and less steep and closer to a horizontal line, it would also represent deceleration. So as I just mentioned on that previous screen, when an object or person is stationary, the line on the graph will be horizontal. And you can see that here. Let's just watch as it happens here. Very good. And what you should have observed is they started at 0, 0. That is, at 0 seconds, they were 0 meters away from the starting line. They then ran for a little over 1 second, not quite 1.5 seconds. And how far away did they get? They got 20 meters away. They got up to this point here. They then stopped. How long did they stop for? Looks like not quite 2 seconds. And then they ran back. And that's what the line going downward means, running towards the starting line. They ran back to the starting line. Okay, so the horizontal line reflects that movement has stopped. Let's think about this here. Can anyone predict what is going to happen? Well, let's get them started back here. Can anyone predict what is going to happen in this graph? Do we have a horizontal line here? Yes, we do. Let's see. All right, so you can see this line was horizontal. So what did they do? They just stayed at the starting line for all that time. They then ran away from the starting line. So now we can move on to looking at speed. Speed is the steepness or the slope of a line on a distance time graph. You can calculate an object or person's speed with the formula distance over time. Now before we delve into that, just take a look at the graph you can see on the screen. And what you will see is you see 4 lines that have different steepness. I want you to watch the man run and see the relationship between the man's motion and the graph that you can see on the screen. And so we can then begin to reach some conclusions about what steepness of a line means. What does it mean if a line is steeper or less steep, for example? So let's watch him run. Okay, what you should have noticed is that for this part of the line, he's running at a constant speed. He gets here, he slows down, he increases his speed, and then he goes even faster. Let's watch it one more time. You can see, slows down, picks up, goes even faster right at the end. Okay, and so what this means is that a steeper line denotes a faster speed. Okay, and now we're going to look at how to calculate the speed based on a distance time graph. To help us do this, I've made a few changes to the graph just so it's easier to interpret for us. The first thing I've done is that I've added a scale over here on the left-hand side that is easier to read. And so what you can see now is that each space is worth 2 meters. I've also added some labels A, B, C, D, and E for each of the points on the graph. In order to calculate speed on a distance time graph, you must determine the rate of change on the graph. This should be familiar to you as you did it in the last section. Remember, to find the rate of change on a graph, you have to identify 2 clear points on the graph. You're then going to draw a right-angled triangle between those 2 points. You will calculate the rise, and then you will calculate the run. So let's do that together with line AB. Line AB, here is 1 point, and here is the next point. I want to clarify that this point here, B, is 111 because it's right in between 10 and 12. Now I have my 2 clearly defined points. I can now do rise over run. I go up and I go over. What was my rise? I went from 0 to 11. So my rise is 11. What was my run? I went from 0 to 1, so my run was 1. Now over here with AB, I'm going to write, what was my distance? My distance was 11 meters, rise. So 11. What was my run? What was my time? It was 1. So 11 over 1, or 11 meters per second. That is my speed. It's the same as rise over run, the rate of change. Let's try BC. With BC, I'm at 111, and I'm going to go up, and I'm going to go over. Now, I want to clarify again, this point here is 217. That's the clear point that I've identified. I went from 111 to 217. So I went, when you think of going up, I went from 11 to 17. What is the difference between 17 and 11? 17 minus 11 is equal to 6. And so my rise is 6. What about the run? I went from 1 to 2. So that makes my run 1. Over here, for the speed for BC, I can write 6 over 1. The distance traveled was 6 meters over 1 second. So my speed is 6 meters per second. So what about CD? CD, I am going from 217 and I'm going to go to 340. So those are our 2 points. Those are our 2 points. Now we can draw our right angle triangle. We go up and we go over. And here we were at 217 and we went up to 40. What's the difference between 40 and 17? 40 minus 17 and we get 23. We went from 2 to 1 and we get, from 2 to 3, that gives us a difference of 1. So we get 23 over 1. 23 over 1, which equals 23 meters per second. Okay, lastly, let's look at D and E. D and E, we draw a triangle. I'm going to go a little bit faster now. We went from 40 down to 0. What's the difference? 40 minus 0 equals to 40. So they traveled 40 meters over how much time? 1 second. So over here, we can write is equal to the distance was 40 meters over the time was 1 second gives me 40 meters per second. Now, if you recall, I could have known and I knew beforehand that the fastest line on this graph was DE. And I could know that because DE was the steepest line. Remember when we saw the man run, we saw that they were running at a constant speed for AB. They slowed down, and we know they slowed down just by looking at the graph because the line is less steep. Their speed then picked up, and then they went the fastest that they went during the entire journey for this last leg, DE, where they went 40 meters per second. Just to clarify very quickly, even though the line is going down to the right, I wouldn't say the speed was negative 40 meters per second, because that wouldn't make very much sense. We don't talk about speeds in terms of negatives. To finish this video off, I'm going to have us look at one more graph and calculate the speeds of the 2 lines that we can see represented on the graph here. So again, we'll label them A, B, and C, and let's find the speed of AB. And if we do that, we're going to draw or identify our 2 points. So here we have 0, 0, and here we have 230. And so we're then going to draw our right angle triangle. Whoops. Our right angle triangle. And we should notice our rise, we went from 0 to 30, so our rise is 30. And we went from 0 to 2, so our run is 2. The distance was 30, so 30 over the time, which was 2. 30 over 2. If I do 30 divided by 2, what I'll get is 15. 15 what? Meters per second. So I just wanted to show you an example where the denominator, the time passed, was more than 1, and where you actually do the division to find the speed, the rate of change per second. Let's look at BC. Again, we're going to identify our points. Here is B, here is C. We're going to draw a right angle triangle. Very good. And from B to C, the run was 2. The rise from 30 to, where is that number there? That number there would be 17. So from 30 to 17, and this gives us a rise of 13. So just to show you how we did that, we did 30 subtract 17, because this here is 17. Think this is 12, 14, 16, 18. This is 17. 30 minus 17, we get 13. So then to do the speed for BC, the speed is going to be 13 over 2. The distance, which was 13 meters, over the time, 2. And we get 6.5 meters per second. So I'm going to end the video there. I will make a part 2 to handle some of the other parts of your handout and give you a hand with them. But this should be quite a bit in order to get you really started. Good luck.